I am Kaisa Miettinen, and I wish you warmly welcome to this demo tutorial devoted to interactive multi-objective optimization and multi-objective optimization in general. This is part of the tutorial series of the demo profiling area, and this is the first one in this spring. There will be 3 more tutorials after this one. And I think we could start a recording, right, Babushka? Okay, so as said, my topic today in this tutorial is multi-objective optimization and in particular interactive methods, but I will be talking a bit about multi-objective optimization with other types of methods as well. And the contents of this talk consists of some concepts, some motivation, classes of different methods that have been developed for solving multi-objective optimization problems, examples of different types of methods, some words about applications, and then some conclusions. The background of the whole consideration in multi-objective optimization is in decision making. And typically, good decisions are characterized by multiple objectives that are typically conflicting with each other. So we tend to say that in life it is impossible to get everything. If you want to buy a house that is down, there was once this kind of a saying that everybody would like to live in one's own house at the middle of the city with all windows facing to the south. That kind of wishes are not possible. We need to typically sacrifice in something in order to gain in something else. And that's what we mean by conflicting objectives. And the idea is that there might be complicated interdependencies among these objectives, and humans need some support in balancing between these perspectives and in order to find the type of solutions that are most suited for the particular needs. And when we formulate optimization problems, we have objective functions that we optimize, typically minimize or maximize. For example, if we are dealing with profit, typically we maximize profit. If we deal with costs, then we minimize them. So which direction is better, it's directly coming from the type of functions we want to include in the consideration. And the decision variables, the functions depend on the decision variables, and by finding the optimal values of the decision variables, we know what actions to take in order to get those good values for the objectives we considered, and that's the basic setting of decision making. Saul E. Guss has said that operations research is a scientific approach to decision making, and we also operations research is a big umbrella term, and multi-objective optimization is part of the field of operations research. And by formulating different relevant perspectives and aspects characterizing the goodness of the decision, as I said in the previous slide, we get different objective functions that constitute a multi-objective optimization problem. And typically, it is easier to formulate these objective functions that represent some perspective than trying to convert all relevant points of view, for example, to be measured in a single function. Sometimes people say, though, that there is no more than one objective in life. It is all about money. but it is not always easy to characterize all relevant perspectives in monetary units. It might be easier to characterize it in units that are more natural to the consideration. For example, environmental values or beauty of some design. They might not be that easy to express in money, but they might be possible to express in some other ways. The idea is that we can reveal the true nature of the problem better in the modeling phase without simplifying too much. And for example, converting everything to be measured by money, it's this kind of there's the danger of missing some information about the true nature of the problem, and might mean some simplifications or on the other hand, overly complicating elements. And by formulating multiple objectives, we get this understanding of the interrelationships, how the objective function values depend on each other, the trade-offs involved. So how much in some function I need to sacrifice in order to get some particular improvement in some other objective. In the multi-objective optimization setting, we can consider this kind of information, and it is typically very insightful and useful. Sometimes it can be even computationally easier to solve multi-objective optimization problems than if we had converted them to some other forms. And one way of getting a multi-objective optimization problem is also possible if we have a lot of constraints limiting the values of the decision variables. And if we have that kind of conflicting constraints that there's actually no feasible solution at all, with traditional means, we have nothing to do, that we can just say that there is no solution to the problem. But if we minimize constraint violations, we get more understanding about how the constraints are conflicting and can find solutions that violate the constraint least. So in that way, we convert each of the constraints into individual objective functions representing constraint violations, and we can balance between constraint violations and get the optimization problem that way. Typically, the task of multi-objective optimization methods is to help a decision maker finding the most preferred trade-off among the conflicting objectives. So the most preferred solution to one's particular needs. I sometimes say that when you have a look at any parking place, there are a lot of cars. They are different sizes, different models, different colors, different ages, and they all have been chosen by the decision maker in question related to one's own needs and constraints. And that's the point of multi-objective optimization, that there typically is no global truth, but there are some nuances that need to be taken into account when solving the problems. I mentioned that operations research is an umbrella term, and under that umbrella we have multiple criteria decision making, which means decision making in the presence of multiple conflicting criteria or objectives, and multi-objective optimization is a subset of multiple criteria decision making problems. MCDM problems also can be of discrete nature, for example, finding the best place for some building or finding the best place for a dumping site or whatever. But multi-objective optimization problems are have functions of variables, as I just mentioned earlier. And I choices in this consideration so that I limit the focus, so that I talk about the cases where we have a single decision maker whom we are supporting, and there could also be several decision makers, but that would then need its own consideration. I will assume that the functions are deterministic. There could also be some stochasticity involved. I assume that I have continuous functions instead of discrete ones, and there are some nonlinear functions involved, because typically in real life, some phenomena at least behave in a nonlinear way, which leads us to the consideration of nonlinear multi-objective optimization. And then one reminder of how do we get optimization problems. Typically, we have some phenomenon application. We can have some mathematical model from which we create a numerical model, from which we make a computational model with which we can simulate that phenomenon with computers. And with that simulator, we can connect optimization and then start utilizing the models in terms of finding the most satisfactory solutions or optimal solutions. It can also be that instead of a mathematical model, we have data, and from the data, with data as a starting point, we introduce models to represent the data, and also from that we get a way to simulate the behavior with computers and utilize optimization. And validation phase can lead to different stages. If sometimes it is the optimization that easiest and best reveals what matters in the correctness of the consideration. If some important aspect is missing, we might need to revisit the model, and only after that we can rely on the results of the optimization tools. But the point is that modeling and simulation are not enough, even though sometimes people make this kind of experiments that they try different options and then they choose the best and they say that I have optimized, but it is not the kind of optimization that I mean. It is something else. So in here we complement modeling and simulation by optimization techniques, but to get meaningful answers and solutions by optimization, the models need to be reliable, and optimization enables making the most of these good models. But optimization cannot compensate shortcomings in the modeling phase. This is something that has to be kept in mind, that optimization plays in the area that the model has developed. And if we think of demo, our profiling area, thematic research area devoted to decision analytics utilizing causal models and multi-objective optimization, we have this seamless chain from data to decision making, and we have different elements in the reasoning. And in this talk, I am considering these parts. So formulating multi-objective optimization problems and utilizing, for example, interactive methods to support decision making. And this can be then related to various different application areas. So the problem formulation, as said, we have several functions to be optimized, and I denote their number by K. And X's are the decision variables that I mentioned earlier that tell us what decision to be made. And these functions typically are conflicting. If there's no conflict among these objectives, then there's no need for multi-objective optimization methods. Normal optimization methods will be sufficient. But as said, in typical normal life situations, we can't get everything. If we improves in some objective, typically it is only possible by necessitating impairment in some other objectives. So we try to minimize all the objectives simultaneously. For the simplicity, in this notation, I have only mentioned minimization. If we have maximization, we can just maximize, convert maximization to minimization by introducing minus. So minimization and maximization, it's just a matter of sign. Minimizing minus f is the same as maximizing f. So that's why I don't deal with minimization and maximization separately. But the idea that we have this decision variables and we have constraints that limit their values, And this is the same as if we had a single function to be optimized. The feasible region would still be determined by constraints. But in addition to that, we have these multiple objectives. And when we map any of these feasible solutions with the objective functions, we get points in the so-called objective space. And in multi-objective optimization, we also pay a lot of attention at this image space. Typically, we do not know this space explicitly. We only know it implicitly via the mapping of objective functions. But anyway, decision space, objective space, they are both important. And the concept of optimality, as I already mentioned, when we have multiple objectives to be optimized, we have different trade-offs. So the concept of Pareto optimality or non-dominance or efficiency or non-inferiority, there are many names for the same because it is such an important concept that whenever we want, so we say that a solution is Pareto optimal if we cannot improve any of the objective function values without impairing in at least one of the others. And this means that we have a set of Pareto optimal solutions that we actually cannot order in mathematical means without some additional information. And here's an example. Even though there are only 2 objective functions in this example, it does not mean that we would be in any way limited to 2, but it's just for the ease of visualization. So for example, here, this is an image of the objective space. We are minimizing both price and maintenance cost. It could be a car or anything that we have these 2 that we want to find the best balance with. And for example, with this orange solution, it has very low maintenance cost, but the price is rather high. And on the other hand, with this blue dot, the price is rather low, but maintenance costs are much higher than in the orange one. So these are Pareto optimal solutions, and so are all these others along this red line. So it means that one can be improved only by allowing sacrifice in the others. For example, if we were outside this red area, then we would be able to improve both the objectives simultaneously. So these are typically the kind of solutions that we are interested in multi-objective optimization. And we can get some, as said, we know this how the feasible region is mapped in the objective space by the objective functions, and we can get some additional information about this set with the help of a so-called ideal objective vector. So a vector in the objective space that consists of the best individual values of the objective functions. So this is the best for maintenance, this is the best for price, and here is the ideal objective vector that tells us the best possible values, so that whoever is dealing with this problem knows that there is no point in trying to get better values for these, but they cannot be obtained simultaneously because they are not this point is not feasible. So we cannot use this ideal objective vector as a solution, but it is supporting information. And the other extreme, the worst possible objective function values in the set of Pareto optimal solutions, they are represented by a nadir objective vector. So basically all Pareto optimal solutions are between the ranges determined by these 2 points. Estimating the nadir objective vector it's much harder than the ideal, but I won't go to that kind of details now. But as said, we have different solutions that can be regarded optimal, and we need some additional information to be able to determine the best solution for individual settings. So that is the role of the decision maker, domain expert, who can express preference information and who typically is somehow responsible for the solution. And in that way, we can then, by utilizing the preference information from the decision maker, we can get solutions that are satisfactory to the needs of the decision maker in question. And if we have a different decision maker, there might be a different best solution, as was in the case of buying cars that I mentioned earlier. And many times we also have another person called analyst who is supporting the decision maker, who knows different multi-objective optimization methods, who is responsible for the other side of the story, so that the decision maker can concentrate on the problem, and he or she is not assumed to be aware of all details of multi-objective optimization or the methods, but the analyst takes care of that side. So decision vectors in the decision space, objective vectors in the objective space, and Pareto optimal solutions in both decision and objective spaces. Here we see the Pareto optimal solutions in the objective space. So there are many concepts. I will mention one more: utility or value function. In many kinds of literature, they say that they assume that we have a utility or value function that represents the preferences of the decision maker. And if this is possible, then it means that we can consider our decision-making problem as the one that optimizes this function. It is a single function, real-valued function, and in that way we would get the best solution for the decision maker, assuming that this function is able to represent the decision maker's preferences and desires. And if the value of this function is the same for two solutions, then it means that the decision maker is indifferent between them. They are equally good. And in many cases, an implicit utility or value function is assumed to be existing, but how to derive this kind of a function from the decision maker so that we could utilize this kind of a reasoning, that is the problem. It is not that straightforward, and it also might be that this function, it is not a global and static function, but because of the decision maker's understanding grows, this function might be evolving. So instead of just thinking of maximizing utility or maximizing the satisfaction with this function, we can think of satisfying the needs of the decision maker by providing different types of preference information, for example, a reference point that consists of desirable values for the objective functions that the decision maker provides. And then we try to satisfy these wishes as well as possible, instead of maximizing some overall utility or value. Because of the central role of the decision maker in the solution process, I like dividing the different methods that have been developed for multi-objective optimization into 4 groups. And in the first one, we do not have any decision maker available. So we need to just find some neutral compromise solution. If we have a decision maker available, he or she can set hopes and expectations first, and then we try to find a solution that meets these needs as well as possible. However, it might not be that easy to provide expectations in advance. They might be optimistic or pessimistic. In a posteriori methods, we generate a representative set of Pareto optimal solutions first, and then the decision maker is supposed to choose one's most preferred solution among this set. It helps from the perspective that in this way the decision maker sees what kind of solutions are available, but it might be demanding to compare a lot of different solutions, and computationally it might be also demanding to create a good representation of the different Pareto optimal solutions. And the more objective functions we have, the more the computation and cognitive demandingness grows. And for that reason, we have the interactive methods. They try to avoid some of the shortcomings of the earlier types of methods, so that we have an iterative process where the decision maker takes part so that the amount of information demanded is limited at a time to be considered, and the decision maker sees more about how realistic one's hopes and expectations are and can adjust them accordingly so that this too optimistic or pessimistic setting would be avoided. We have also two types of methods. The basic MCDM world derives from the school of thought of mathematical optimization. So we have optimality conditions characterized for multi-objective optimization problems. So we know under what kind of assumptions Pareto optimal solutions exist, and many of these type of methods base on scalarization. So the multi-objective optimization problem is converted into a single objective optimization problem, which can then be solved by an appropriate single objective solver. And by choosing the scalarization function carefully, we can still guarantee Pareto optimality. So there can be theoretical proofs about optimality, but of course the other side of the coin is that to be able to make this kind of a theoretically sound reasonings, we need to set a lot of assumptions. But in the MCDM side, the decision support aspect and utilization of preference information, they have a long history, and a lot of different approaches have been developed. Then the other type of methods is nature-inspired methods like evolutionary algorithms. I'm only now talking about those. There are also other nature-inspired algorithms, but anyway, the basic idea that they are heuristics. So they cannot guarantee optimality as in these theoretically sound approaches, but on the other hand, they can solve problems that do not satisfy these requirements that need to be met to be able to have theoretically sound reasoning. So evolutionary multi-objective optimization methods deal with a population of solution candidates that are manipulated with different operators, and the idea is to try to manipulate the population so that it would be getting closer and closer to Pareto optimal solutions, and that would be providing a better and better representation, so being as diverse set as possible, covering the Pareto optimal set well. The problem with heuristics is that there typically cannot be any guarantees for optimality, and that's why the performance of these type of methods is typically judged by studying how they perform with different benchmark problems. For these problems, we know what the Pareto optimal solutions are, so that we can measure the satisfaction or the success of the method by seeing how close the found solutions are to the true optimal solutions, and how good the representation is. So they can be applied to demanding and difficult problems for which the mathematical optimization methods are not well suited, and there are some differences in the terminology. I won't go to that kind of details there, but anyway, these are two types of approaches that basically try to address the challenges of multiple conflicting objectives. And the history of evolutionary algorithms is shorter than mathematical optimization, but the focus in the early years was in a low number of objective functions where the role of the decision maker was not that much emphasized, and they were more on the technical side, but more in recent years also the decision making aspect has been gaining more interest in this field, and also incorporation of preference information has become of interest also on this side. I mentioned this word scalarizing function earlier, so it is something that is one of important mechanisms. So we have the original multi-objective optimization problem that we have carefully formulated, and then we combine preference information to it, and get a scalarized single objective optimization problem. And by choosing the scalarizing function carefully, we can guarantee that we get a Pareto optimal solution to the original problem. And of course, we need to use the appropriate single objective optimization method to solve this problem. But not any scalarizing function is equally good. As said, we need to choose carefully, and the desirable properties are that the Pareto optimality is guaranteed. So we get Pareto optimal solution and we don't miss any relevant Pareto optimal solution because of the weaknesses of the scalarizing function. So as examples of different types of methods, I have a few. The method of global criterion is an example of methods where there is no decision maker available. So as said, we can identify the ideal objective vector without any human involvement. And for example, in this case, once again, we have two objectives to be optimized, and this bold line represents different Pareto optimal solutions. And we can, for example, minimize the distance from this ideal objective vector to Pareto optimal objective vectors. And by using LP metrics, and changing the p-value, we get a different solution. So by the choice of the metric, we, for example, in this case, would get a very different solution. Alternatively, we can take some, for example, the ideal and nadir point and take their average and project it to the Pareto optimal set. That's another way to get a solution without the involvement of the decision maker. But in this case, there's not much more one can do because additional information is not available. As said, a posteriori methods generate a representative set of Pareto optimal solutions so that the decision maker can then choose from them. But the higher the dimensions are, the more computational cost will be needed to create a good representation of the solution set, because in higher dimensions, sets of solutions become extremely sparse. And then there's this human element, how to see the solutions in a way that one can compare them without being too much cognitively loaded. Weighting method is one of the most widely used multi-objective optimization methods. So, and this method that has been invented numerous times by different people. So the idea is that you create this kind of a scalarized function. So you give a weighting coefficient for each of the objectives and you optimize the weighted sum. Typically, we scale the weights so that they sum up to 1, but this is just technicalities. But anyway, the weighted sum is a method that should be used with utmost care because it can somehow work for convex problems, but for example, non-convex problems, there can be solutions that will never be found no matter how this weighting coefficient is chosen. So in other ways, referring to what I said earlier, weighting method, this function is not a good scalarizing function because there can be solutions that are missed, not because they don't exist, but because the method cannot find them. And at this stage, I want to give you another example about the dangers of applying a weighting method. This is a problem that a colleague of mine, Pekka Korhonen from Aalto University, originally proposed many years ago. This is a discrete problem for simplicity. So we have a wife selection problem. So we have 3 candidates and we have 4 objectives that characterize a good wife. The candidates have been judged based on how they perform. So Mary is very good at cooking, housewifery, and tidiness, but not really beautiful. Jane is kind of in the middle in terms of all these objectives, and Carol is a beauty queen, but hopeless in other respects. So don't be upset if this is kind of this sounds rude that, oh, wife selection is an optimization problem. I just want to make a point, and with this example, one can make the point clearly. So if we apply the weighting method to solve this problem, we need to provide weighting coefficients for each of the objective functions. And as said, we assume that they sum up to 1. And let us, for example, assume that we want to emphasize beauty, but the other objectives are also somewhat important. So we have this kind of weights. And when we apply the weighting method, we calculate the weighted sums for each of these solution candidates, and tada, because higher value was better in these qualities, we get the best value for Mary. Mary is the winner. Even though Mary was the worst, in that objective that was regarded to be the most important, that was given the highest weight. So the lesson to be learned here is that the weighting method is not necessarily a good method if you want to somehow understand and control how your preferences influence the solutions that you obtain. And in this case, sometimes people say that, okay, let me try to change the weight so that I would get some other solution for the problem. But that was not the point. The point was not to find the best weights. The problem was to find the best wife. So it is not that easy to control the solution process with weighting coefficients. And as said, this problem with convex and non-convex problems exists as well, so that if we apply the weighting method, we can only find these solutions here and these solutions here. We will never find these solutions even though they are Pareto optimal, and still some kind of a balance between the objectives located here might still be very good for the decision maker. So the role of the weights is not that easy to understand. And on the other hand, small changes in the weights can lead to dramatical changes in the objective functions. For example, if we are somewhere here and change the weights just a little bit, we will jump here. And this will give a very misleading interpretation of what kind of solutions are available to the decision maker. And evenly distributed weights do not guarantee that we would have an evenly distributed representation of Pareto optimal solutions. So this was just an example to show you that why we need other multi-objective optimization methods, why applying weighting method is not enough. Another method, very simple method that is very widely used, is epsilon constraint method, where we choose one of the objectives to be optimized and we give bounds to the others. So this is another way to convert the problem to a scalarized problem. In this case, we don't have that serious shortcomings as with the weighting method related to convexity. So we can find any Pareto optimal solution by just adjusting these bounds in an appropriate way. But it is not always that easy to provide these values in a meaningful way, and some attention will be needed to get a good representation. But this method is in principle a better choice than the weighting method if we have a non-convex problem. On the other hand, by using this method, we lose the chance of studying the trade-offs. So we need to change the problem every time when we change these right-hand side values, and this kind of a study of what kind of sacrifices would lead to what kind of improvements. It's somewhat clumsy, but possible. Another method is method of weighted metrics. So compared to this method of global criterion, we introduce weighting coefficients into these norms where we optimize the distance to the ideal objective vector, and by changing the weights, we can get different solutions. Excuse me. One more alternative is achievement scalarizing function, where we have a reference point as a way to provide information to get different solutions. Reference point can be provided mechanically, or it can be coming from the decision maker. If it comes from the decision maker, it means that we have desirable values for each of the objectives as the components of the reference point. And we can formulate different achievement characterizing functions utilizing different types of reference points. We can have these desirable objective function values. We call them aspiration levels. On the other hand, we can also have information about the values that the decision maker would like to avoid, so that not at least getting any worse than that. So there can be two types of reference points in achievement characterizing functions. But anyway, the whole idea is to project the reference point to the closest Pareto optimal solution. And by changing the reference point, we get a different solution. And here is an example how this works. Here's an example formulation. And here we have a problem with, once again, with two objective functions where we have these red lines, in this case, representing Pareto optimal solutions. And here we have a reference point A, which is feasible. So we can improve from the values that we have in this point. So the achievement characterizing function, as said, it projects to the closest Pareto optimal solution. So we would get this solution. And what is the direction of projection? It is determined by these weighting coefficients. In this case, this is very widely used. So we use the difference of the nadir and ideal objective function values as a weighting coefficient, so that this also takes care of the scaling, so that if different functions have very different magnitudes, this kind of a coefficient improves the functioning of this scalarizing function. But so it works if the reference point is achievable, and it also works if the reference point is unachievable, like in case of B. So once again, it projects the solution to the closest Pareto optimal one. So this function works for independent of the problem being convex or non-convex, and also if the reference point is achievable or not. I mentioned some words about evolutionary algorithms. I will not spend much time on those here, but as said, they are common meta-heuristics that are good for mathematically difficult problems, and the population tries to come up with an approximation of a Pareto optimal set. And in a way, there are two objectives that these algorithms try to achieve simultaneously. So as diverse set of solutions, and all these being as close to Pareto optimal as possible. The optimality cannot be guaranteed, but that's the idea that if we have here a population with evolutionary operators, we manipulate it so that the next generation of solutions, the next population would be more diverse and closer. And by repeating this, we would get closer and closer to getting a good representation of this red area. The other thing is that they are, in this basic form, they are also members in this a posteriori type, so they represent the whole set. But if we have many objective functions, we need to have more and more elements in that population, and it gets more and more computationally time-consuming and demanding to apply these algorithms. And there might be many areas of the Pareto optimal solution set that are not at all interesting to the decision maker. So we are kind of wasting effort in representing them. So that's why we can also introduce some preference information in these algorithms to focus the search to some area and not the whole Pareto optimal set. And special evolutionary algorithms have been developed for problems that have more than 3 objectives. So-called decomposition-based methods have been developed there, and many of them also utilize scalarizing functions that are similar to the ones that have been applied in the MCDM side. And more hybrids of these different types of methods are nowadays proposed. So in the a priori type of methods, the idea was that the decision maker provides hopes and expectations first, and then we find a solution that meets them best. And the value function method is a simple one, assuming that we have this value function. As said, we just optimize it, and then that's the solution. The tricky thing is how to get this function. But if this function we have, then it represents the global preference structure of the decision maker, and we know what is best. But how to get there, that we would have this function formulated, that's the problem. And there are some assumptions made. For example, if there are some solutions that are incomparable, this kind of function cannot represent that kind of situation. So if we assume that we have a utility or value function, it implies that we assume that all solutions are comparable. And in that case, if we have this first the feasible set and its image in the objective space, we map it to real values, and we very nicely can order different solutions and get the best one. But the problem, as said, is that how to get the function value. So we need some other tools as well. Another simple a priori type of method is lexicographic ordering. If we can say that we have an absolute order of importance of objectives, so that this function is much more important than the other one, we can solve the functions lexicographically. So first, optimizing the most important function. If it has a unique solution, that's the end of the story. If the most important objective function has alternative optima, we optimize the second most important objective function in that set and continue as long as we have alternative optima. Some people like making decisions this way, but this is really rough because this absolute order of importance is not always easy to provide. And on the other hand, it is very likely that these less important objective functions would not be playing any role in the solution process. But anyway, even though they are not all equally important, they might still have some relevance in the solution. So in this way, this is kind of a rough, and trading off is impossible because the starting point is this absolute order. As I mentioned at the beginning, I like to spend more time with interactive methods because they try to avoid some of the shortcomings of the previous methods. So we have a decision maker, problem domain expert, and we are involving the decision maker in the solution process in an iterative manner, so that the decision maker in a way directs the search with one's preferences. And in that way, we want to find a solution that the decision maker finds the most preferred. And by involving the decision maker in this kind of a iterative manner, it means that we need to find the type of information to exchange that is understandable to the decision maker. The decision maker needs to understand the question so that the answers could be meaningful to be applied. So the decision maker, as said, can find the most preferred solution by directing the search with one's preference information and move around, for example, move around in the set of Pareto optimal solutions, guiding the preference information. The important thing is, as they said, that the question should be understandable, and one thing is enabling learning. So if we make too strict assumptions to begin with, so that assuming that the decision maker knows all that one wants from the beginning, it makes the solution process nicely convergent, but it might not make it possible to learn, which is very important for decision making, not only to find a solution for the problem, but also to learn about the problem, and in that way gain confidence in the goodness of the solution. We have a really big number of different interactive methods, but as said, they are iterative, so there's some pattern that is repeated, and preference information is asked for between these iterations, and some information is provided to the decision maker after each iteration. And because of this kind of a nature, interactive methods are appropriate only in cases there is a decision maker available who can and wants to spend some time in the solution process. But in that way, we only generate those kinds of solutions that are of interest to the decision maker. So we don't waste computationally resources in other kind of solutions. And because we keep the amount of information limited per iteration, the idea is that we don't overload the decision maker with too much information at a time. As said, the most important thing of interactive methods is the support in learning, because once the decision maker has provided some hopes and expectations, and once one can see how they were able to be met, one learns about the trade-offs, one learns about the phenomena involved, and one can also adjust one's own hopes based on this growing understanding. And this increases the confidence in the final solution, because one then knows why one has chosen some particular solution, and can also justify it to others. So the methods differ in terms of what kind of preference information is used, so what is asked from the decision maker, what kind of information is given to the decision maker during the solution process, and how solutions that reflect the preferences are generated. So this leads to very different kinds of interactive solution methods. So at each iteration, the decision maker sees some information and provides preferences. And the understanding of the feasibility of the preferences grows together with the understanding of the problems, the limitations and possibilities of the problem. And this can lead to new knowledge, understanding about the behavior of the problem and phenomena better, and finding hopefully solutions that could not even be considered before. And of course, because the active involvement of the decision maker, the user interface plays an important role in interactive methods. Here is briefly the core structure that is typical to many interactive methods, not necessarily every single one, but first we initialize the solution process and calculate some supporting information, for example, information about the ranges of the function values in the Pareto optimal set as the nadir and ideal objective vectors. Then we get some starting solution. It can be a method-specific subproblem to be solved, or it can be some initial Pareto optimal solution that comes from the decision maker that we have just guaranteed to be Pareto optimal. Anyway, we somehow get the solution process started and ask the decision maker to provide preferences to indicate what kind of solutions would be desirable. Then we create these solutions in the way that the method in question does it, show them to the decision maker. Depending on the methods, we create one or several solutions, and then the decision maker decides whether one is happy with some of those or whether one wants to provide new preferences and keep iterating in the loop. In interactive methods, we can in interactive solution processes, we can identify many times two phases. So first, in the learning phase, the decision maker explores what kind of solutions are available, what kind of trade-offs there are, and learns about the feasibility of one's hopes, and can change the hopes and desires and preferences to get a rough understanding of the solutions available, and then eventually aim at identifying a region of interest, some part of the Pareto optimal solution set that is most appealing, and then a decision phase, which is not anymore this kind of a searching in kind of a in terms of very different solutions, but but converging in that region of interest that was identified towards the end of the learning phase. And in that way, the decision maker eventually identifies the final solution in the region of interest. Of course, if some more learning still takes place here, one can of course always get back to the learning phase and start making more radical changes in preferences if one so desires. But as said many times, we can identify this kind of phases when we follow the solution process of decision makers. Examples of preference information are, for example, so that we give a small set of examples of Pareto optimal solutions to the decision maker to choose from, or so show which of these solutions you like most, or in the opposite case, show which of these solutions you don't like at all. So what kind of solutions you would like to avoid. One can make pairwise comparisons between different solutions. One can express desirable values as components of reference point, as I already mentioned, or desirable ranges for objective functions, so upper and lower bounds for objective functions that are desirable. One can classify objective functions. I will soon give an example about what this could mean. One can provide opinions related to marginal rates of substitutions or desirability of trade-offs. There are many different opportunities here or combinations of these. And there might be also at some point a need to change the type of preference information during the solution process, which should also be enabled. But here I provide some examples of different interactive methods based on the different types of preference information. Chebyshev method, it creates different Pareto optimal solutions, and the task of the decision maker is just to select which of the ones one likes most. And then the search concentrates around that kind of solutions. And the comparison of the solutions is the only task for the decision maker, and the decision maker determines how many solutions one is able to compare, so that the number of solutions does not exceed the desired amount. And here the easiness of the comparison, of course, depends on how many solutions that the decision maker wants to compare and how many objectives there are. So how many components in each of the objective function we have that are to be compared. And some convergence is expected from the decision maker. So if at some point the decision maker has not liked some kind of solutions, one cannot later say that I would like to get to that kind of solutions. We are assuming some kind of convergence. So if this kind of thing happens, then the decision maker needs to start from the very beginning. And there's quite a lot of underlying calculation needed to create that representative small set of solutions to the decision maker. So in a way, computing resources are wasted, but of course, parallel computing can be utilized. And here's one way of generating the solutions, but I won't go to that kind of details. Another method is reference point method, which uses the reference point as preference information, as the name suggests. So the decision maker provides desirable values for the objective functions, and this point is projected onto the set of Pareto optimal solutions with the achievement scalarizing function that I introduced earlier. And in addition to that, the reference point is shifted to coordinate-wise, so that we get k more solutions corresponding to the shifted reference point. So k stands for the number of objective functions here. So in that way, the decision maker gets k+1 solutions to compare and provides reference point as preference information. And here's the idea in brief. So if the reference point is close to the Pareto optimal solution set, it kind of is assumed that the decision maker is aware of what kind of Pareto, what kind of solutions are feasible. So then we, by shifting the reference point, we get a fine-tuned representation of solutions nearby. If the reference point happens to be very far, then it shows that the decision maker doesn't really know what is feasible. And then by shifting the reference point, we get a more rough idea of different solutions. And then the decision maker provides new reference points as long as one wishes, but there's no consistency required. On the other hand, there is no support in providing the new reference points either, but very different type of interaction with the decision maker compared to the previous one. Then Nimbus is a method that has been developed in our group, and the idea there is that anyway, dealing with the objective function values is understandable to the decision maker because objective functions should have a meaning compared to, for example, the weighting coefficients that I mentioned earlier that don't have a direct connection to the function values. So in Nimbus, the decision maker provides preference information in terms of classification. So one sees current parrot optimal solution and indicates what kind of changes in the function values would make the solution more preferred. And this reminds the decision maker constantly about the trade-offs, because one can only get improvement in some objective functions by allowing some relaxations and that is sacrifices in some others. And in this way, the decision maker learns more about how achievable one's desires are. And of course, the search stops if the decision maker doesn't want to improve or allow impairment in any objective functions. There are possibilities of saving interesting solutions and returning to them later, taking some of these as a starting of the classification. I mentioned the role of scalarizing functions earlier. Nimbus has its own scalarizing function, and the choice of the scalarizing function underneath the solution method leads typically to different solutions, even though if the preference information is the same. So that is why we have the so-called synchronous Nimbus, which contains up to 4 different scalarizing functions. So based on the preference information in terms of classification that the decision maker once provides, we can create several scalarizing functions, solve them, and get somewhat different Pareto optimal solutions, and let the decision maker choose which of them is the best, instead of us method developers determining in advance which scalarizing function should be applied. So synchronous Nimbus is the kind of Nimbus that we typically nowadays use. It provides this opportunity. Of course, if the decision maker wants to only see one solution per each type of preference information, it is still possible. And there's also an option of creating intermediate solutions between any 2 Pareto optimal solutions, so that the decision maker can provide different types of preferences depending on what is desired, and learn during the solution process, and only study Pareto optimal solutions that are of interest to him or her. So the classification, we have up to 5 classes available. So as said, the decision maker sees the current Pareto optimal objective vector, and for each of the components, for each of the objectives, the decision maker says whether one wants to improve, that is decrease the function value as much as possible, or improve but only till some bound, or whether the current value is satisfactory, or whether one allows the function value to get worse till some bound to make space for some others to get better, or whether one allows some function to change freely to see what kind of changes would take place in the other objectives. And some of these classes can be empty, but there has to be something to indicate what kind of improvements one wants to make and what kind of sacrifices one wants to make. Otherwise, it's not possible to move away from the current Pareto optimal solution. And we have different implementations. We did a World Wide Web implementation of Nimbus already in 1995, when World Wide Web was a very novel and new thing, and this was very first unique interactive optimization system that was operating over the internet. So centralized computing, distributed interface were the key words. So no need to install any software, no need to worry about the appropriate compilers or operating systems. This is not the implementation of 95. A little bit more recent implementation is still available for kind of a teaching purposes, for example. But then we created an industrial Nimbus version because in those days, companies said that they don't want to send their information over the internet. They wanted to have the software in their own premises. So we created in Nimbus, which was easy to connect to different simulation tools or that would be then needed to evaluate objective and constraint functions. And we had different options there. In Nimbus still exists, but we have shifted our interest in developing an open source software framework, Desteo, which also contains Nimbus methods, but also other interactive methods, and it is under construction. So more features are being introduced there. And here is the homepage of Web Nimbus. As said, it is still available and one can visit it as a guest without signing in, so one can easily get to see what is available. Here is the classification window of Web Nimbus. So by clicking with the mouse at different parts of the bar, one can indicate the desired values, how to, for example, in this case, the bar value was here, and the decision maker clicked here to indicate that one is willing to sacrifice a little bit for this function to get improvement in the others. So this was very advanced technology in those days to have this kind of a interactive way to provide preferences. And then these are different ways to visualize different solution alternatives in Web Nimbus. Here is a user interface of eNimbus. So still the bars represent the current objective function values, and one can click in the bars to indicate whether one wants to improve the current value or allows it to get worse. So the classification takes place in this kind of implicit manner. And then here bars starting from the right, they refer to functions to be maximized, and from the left to be minimized. So the less color there is, the closer the current value is to the best possible value of that particular function. And eNimbus also has different visualization opportunities to compare the solutions generated if the decision maker wants to utilize those. So far, I have talked about interactive methods that deal with Pareto-optimal solutions, but one can also think of it in another way. Because of the trade-off, it might be that the decision maker might be unwilling to move around from the starting point because of the pain in sacrifices. And this is this corresponds to the so-called prospect theory of Kahneman and Tversky, when they studied that humans are not reacting symmetrically to gains and losses, but typically losses are always more painful than how satisfying gains are. So sacrifices might hinder the decision maker's willingness to move around. On the other hand, our past experiences affect our hopes. And there might be also anchoring taking place, that we fix our expectations to the starting point, but that we see that, and we are not able to really be open-minded to other opportunities. And that might be all leading to the fact that the best solution is actually not found. And this can also be a case in group decision making, where we have different interest groups, and if one interest group needs to sacrifice in something that is important to them in order to make space for some other interest groups to get some improvement in values that are important to those, this might be a very fruitful starting point for discussions. So in Nautilus, based on this reasoning, we start something from something bad. So from a nadir objective vector where there's no interest in getting stuck there, no interest in anchoring there, but enabling movement so that all objective functions can improve simultaneously. No need to consider sacrifices. We always get something better. And eventually we move to the Pareto optimal solution. So the final solution will be Pareto optimal. That is not something that we question, but we question the way we reach that solution. And in that way, the decision maker can freely approach any part of the Pareto optimal set. And we have different variants of Nautilus methods that allow the decision maker to control the movement differently. But here's the idea, once again, with a bi-objective problem. So these are the Pareto optimal solutions, and here is the starting point, the nadir point. And basically from this point, we can reach any Pareto optimal solution. But the decision maker provides some information about the direction to move. And then we take a step towards that direction. And this naturally means that these values of objective functions that can still be reached from that point without sacrifices shrinks. So the closer we get to the set of Pareto optimal solutions, this reachable area shrinks. And if at some point the decision maker feels that now I lost something that I would still like to reach, so one can always go backwards and widen up the reachable ranges. But that's the idea, that eventually we then converge to a Pareto optimal solution, but no need to be thinking of sacrifices on the way to get there. In this solution type, we lose the connection to the feasible decision variables during the search, but we know that there always exists a Pareto optimal solution also in the decision space that is better than what we show to the decision maker. So there will be not kind of surprises from that perspective. But the idea is to avoid forcing the decision maker to think of trade-offs. So it's a new perspective to solving the problems, and it frees us from the danger of anchoring, and it can be the final solution, or this can be also used as a means to find a starting point for some other interactive method if one then wants to use a traditional method that deals with Pareto optimal solution once we have made sure that the starting point is chosen well. Another important element behind the requirements set for multi-objective optimization methods is the computational cost element. I have touched this very briefly so far, but it might be that, for example, objective and constraint function values can be only evaluated by calling a simulator, and the function values are derived from the output of a simulator. And the simulation models might be really time consuming. There might be, for example, partial differential equations to be solved, and this might take time. And in that way, the interactive nature of the solution process tend to suffer if the decision maker has to wait before one gets solutions of interest. And in that case, it makes sense to pay attention to the computational cost. And one way is to train a computationally inexpensive surrogate or meta model to each of the expensive functions and solve the problem where these surrogates are used instead of these original functions. There are evolutionary methods that have been following this reasoning, also an interactive one, but here I now talk about other types of approaches for dealing with the computational cost matter. The other thing, this is related very much also to demo, because fitting meta models is done if we have data and we want to create an optimization problem. If the starting point is data instead of simulation models, we also in that case can utilize some of these approaches mentioned. So there's a connection that way. And basic idea is that we can hybridize good properties of different methods to utilize their strengths and avoid their weaknesses. And for example, the strength of a posteriori methods was that we get some kind of information about the different Parrot optimal solutions. And we can combine ideas of a posteriori and interactive methods to provide more information about the Parrot optimal solutions to start with, and then utilize the strengths of interactive methods in terms of allowing learning and concentration on small amounts of information at a time and saving computational costs. So some hybrids of a posteriori and interactive methods next. And in principle, we can see it as a kind of a three-stage process. So first, we apply an a posteriori method, which does not need the involvement of the decision maker. So if this takes time, it does not matter that the decision maker is not waiting. Then we create a surrogate based on this output of the a posteriori method. And then we involve the decision maker and in solving that surrogate problem, which is then computationally inexpensive to solve, and the decision maker can take part and apply an interactive method. And then in the third stage, post decision making, we can make sure that the solution is Parrot optimal. For example, if the a posteriori method was such that it was not able to guarantee optimality, we can do some projections in the third stage. But the decision maker is only involved in this stage that is not involving computationally expensive calculations, no waiting times. One example is navigation-based method. We have Pareto navigator, non-convex Pareto navigator, as the name suggests, for convex and non-convex problems, where we first, of course, we have the actual Pareto optimal set, but we also introduce an approximated Pareto optimal set by applying first an a posteriori method and creating an approximation to the Pareto optimal set, which is then something that we can navigate in real time, so that the decision maker sees in real time the kind of trade-offs between the objectives, and one can direct the search with the help of a reference point, so desirable objective function values. So we don't approximate individual objective functions, but we approximate the set of Pareto optimal solutions directly. And here is a kind of a user interface window. Here's the output of the a posteriori methods solution set, and based on this we create an approximation, and then this is the starting point that the decision maker chooses, either from these ones or in some other ways, and then these blue horizontal lines represent desirable function values. In this case we have 4 objectives, and when the user pushes this button, one starts seeing how these bars evolve and sees the history of how the function values have been evolving, can stop at any time and provide new desires, and in that way literally navigate in the approximated Pareto optimal set. And one can always then project the approximated solution to the original objective function values, but this projection might take a little time because then we need to call the original functions. But anyway, this is also possible because as the name suggests, approximations always involve some error. But here's the idea in brief. In 3D, here we have the set of objective vectors in the objective space. We have taken these black dots as they are the outcome of the a posteriori method. So we create the approximation with them, we get, in this case, we get this polyhedral set, and then the decision maker can move around in this set conveniently and see, as said, in real time the trade-offs of the objectives. E-Nautilus method is also similar in terms of first creating a set of Pareto optimal solutions or representation with a posteriori method, then applying Nautilus thinking, and then having the projection step. And for example, here's the idea that the decision maker can say how many solutions one wants to see. So for example, in this case, the decision maker has said that one wants to see 6 solutions. So these 6 points would be shown to the decision maker, and then if one, for example, chooses this one, we would go to that one and show the next 6 ones in that region that has now been shrinking from where we started. And here's a screenshot how to visualize this in the user interface. Nautilus Navigator is one more method that combines ideas from the Nautilus philosophy and the navigation kind of a user interface, so that once again the decision maker can in real time see the changes. But in this way, the idea is to show the reachable ranges, how they keep shrinking when we approach Pareto optimal solutions, so that the preference information, once again, is desirable function values, and one can also provide some bounds. And once again, as in the other cases, the decision maker can always go backwards if one wants to change the direction of movement, but it is easy to see the progress made. And we have also a YouTube video of Nautilus Navigator that you can watch if you like. But here's a case where we have 3 objectives, and we have, once again, these blue lines represent these desirable values, aspiration levels, components of the reference point that the decision maker has provided, and we can see how the reachable ranges have been evolving. And the decision maker has stopped here. One can go backwards, or one can change the aspiration levels and then continue whenever one wants to. And the nice thing is that in this kind of a user interface, one can see the history. One does not have to remember what one saw in the past, but it's all visible. And here is the case when the decision maker provided some new references, and then eventually we reach the Pareto optimal set, so we get a single solution once we let this run till the very end of the search process. So that was a set of different examples of Pareto optimal of interactive methods to deal with Pareto optimal solutions in different ways that involve different types of preference information, and some experiences with domain experts, decision makers. Typically, they like interactive methods a lot. In many cases, when we have introduced interactive methods, it has been the first time when they concretely see the conflicting perspectives simultaneously, and they appreciate the ability to learn about the conflicting properties in that concrete way. Of course, they are domain experts. They know about the conflict, but having this kind of an opportunity to really see how the functions are interdependent has been very welcomed. And this new insight that can be obtained has been appreciated. And the type of preference information in terms of classification or desirable reference points, they have been found understandable, and typically the people have been satisfied with the solution, and they have been confident with the final solution. Of course, the decision makers' role, how to judge the goodness of the solution, in this we need to rely very much on the opinion of the decision maker, but the feedback has been very, very positive indeed. And as mentioned, there is this visualization element that, in particular with interactive methods, is emphasized. This is just a teaser that there will be a talk given by Jus later this spring when he will go to more details of visualization, but they are just an important element in supporting, in particular, interactive solution processes, but also other types of solution processes. But I won't go to these kind of details now. Instead, I will say a couple of words about applications. We have the beauty of this kind of methods is that they are application independent as such. So it doesn't matter to the method what the functions involved actually are representing. So examples are in chemical process design, in e-heat exchange network synthesis, intensity modulated radiotherapy treatment planning, wastewater treatment planning and plant operation, data-based forest management, optimal design of permanent magnet synchronous generators, optimal design of air intake ventilation systems, tractor cabins, energy system design of buildings, many kinds of things one can consider. And a few words about some other cases in more detail. For example, in this case, we had a hierarchical structure. It was about designing an operation of a paper machine. So two levels, a bi-level problem. Both these levels have different objectives, and so multiple objectives on both levels. And the point was to balance between all these. And we applied some model predictive control elements in this, but the multi-objective optimization provided a good means to control these complicated interdependencies. This case or designing related to the head box design in paper machines. Head box is at the beginning of a paper machine. It is the kind of unit that distributes the combination of water, wood fibers, chemicals, and fillers to the length of the paper machine. So the rest of the paper machine just gets rid of water. So what happens in the head box matters a lot in terms of the quality of the paper. And when we started dealing with this problem with an interactive method, they had identified 3 objectives, and they had applied already an evolutionary algorithm and the weighting method. But by applying an interactive method, it became apparent that actually one of the objective functions had not been formulated correctly. But these kind of methods that they had been applying earlier, they had not revealed this problem, but the interactive nature helped them to find this problem and reformulate and then get satisfactory solutions. So this is one of the important things of applying interactive methods, that you can also utilize it as a means of verifying the goodness of the underlying model. In the ultrasonic transducer design case, there were 3 objectives identified, and even the starting point of the in-Nimbus software that we were applying then was better than their current design when they had not been so explicitly considering the objectives earlier. So all that we could do with multi-objective optimization was pure improvement. In the optimization of the wastewater treatment process, the case was that they had the idea that they need to convert all the objectives into money so that they would have a single objective. But for example, one of the objectives was related to energy consumption. So minimizing energy consumption was desired, but to convert all energy consumption into monetary units, you need to make forecasts of how the energy price would be evolving in the future, which introduces a new level of uncertainty. By considering energy consumption as such, we can avoid that kind of overly complicating matters and balance between the objectives in their true nature and we got very satisfying and very good solutions. In brachytherapy, this is a kind of an example of a different field of life. The problem is that there is a radiating device that is installed inside a human being. And the question is that there's a kind of a tube and this radiating element is moving in that tube. And the question is how long it will be staying at one spot, how fast it will be moving, and controlling this is important because we want to treat a lot of the cancer cells, but do as little damage as possible to the healthy tissues and sensitive organs. So clearly multiple conflicting objectives that interactive multi-objective optimization introduced a new perspective to. And continuous casting of steel is an example of the cases that I mentioned earlier, that there was a set of constraints that were conflicting and there was no feasible solution. And by converting the constraints into individual objective functions of constraint violation, we could actually understand more and find out that actually there was only one constraint that had to be violated to get meaningful solutions. So that's all that I wanted to say. I just wanted to remind that we have this open source software framework development DESTEO. It contains interactive methods of different types, scalarization-based methods and evolutionary-based methods. It is under development, and the main thing is that everything is open source and Python. And this concentration of data-driven decision support. Also in an academic project, we are extending this DESTEO framework to be more applicable to problems that are relevant to demo. We are also interested in developing automatic decision makers and quality indicators for interactive methods, visualizations of different sorts, explanations and applying means of artificial intelligence in different stages of solution processes, and inspiration comes from different challenges of real-life applications. So to conclude, decision-making typically necessitates considering multiple conflicting objectives simultaneously, and the more complex the systems are, the bigger is the need for decision support, and that's what we can provide with multi-objective optimization methods, and consider the interdependencies as an entireness instead of some parts or some objectives individually, which would easily lead to only suboptima. And there are still many application areas where we need to increase the awareness of the fact that multi-objective optimization problems can be solved. There is no need to force the problem to have a single objective already in the modeling phase. It can be then done later on in the solution as a part of the solution process, but by introducing the conflicting objectives, we really have a chance to learn about the trade-offs and gain understanding about the problem. And the beauty of interactive methods is that the decision maker learns and gains understanding about the problem, and if the decision maker is available, it is very recommendable to apply interactive methods. If this is not the case, then there are many other methods that one can also apply. And then my motto, compromise is better than optimum, because by a compromise, even though it has a negative tone in layman's language, it means that by making a informed choice among the conflicting objectives is much better than just optimizing one perspective and ignoring the rest. There are still a plenty of applications that would benefit from this kind of support, and hybridization of different method types has a lot of potential. Because I have been saying so much that there are so many different methods, so the question of choosing the method is an important one, and basic perspectives to this answering this question is coming from the properties of the problem involved, availability of the decision maker, and if there's a decision maker available, the type of preference information that this particular decision maker is comfortable in providing. I would like to thank the whole multi-objective optimization group and all collaborators who have been involved in this development over the years, and of course, funding agencies. And finally, a reminder that we have an International Society on Multiple Criteria Decision Making. If you are interested in these topics, the membership fee that does not exist, so it is free. There is a website, there is a newsletter, and different activities. For example, International Summer School, it was postponed from this summer, from last summer to this summer. Let us hope that it can be realized. But the international conferences we have typically had every 2 years, but this year's conference they have decided to postpone till next year because of the pandemics. But anyway, this society can provide nice forums for exchanging ideas and learning more. But now I would like to thank you warmly